All right, welcome to AA1-7. I don't know why that says just A, to be honest. Add that in there. AA1-7, finding exact equations. For the warm-up, finding the exact equation of this graph, we start with the type of graph it is. Starting low, doing that little change, and then moving forward, but not going up very much. That is if you check with your parent graph toolkit, that is a cube root function. And that parent graph is y equals the cube root of x. So this one has been moved. As you can tell, we now have a locator point of 6, 2. So we can add that part into our parent graph, into our general equation. So y equals a times the cube root of x minus 6, and then plus 2. And I don't like how that looks, so I'm going to erase that part and fix it. So the part that we don't really know or aren't sure about just yet is the a value. So with that, what we need to check and see is if, like all the other parent graphs from the locator point, we go over 1 and up 1 and have a point. In this particular case, we do. So we know that in this case, our a value is 1. Or we can also just leave it blank, because 1 times anything is just itself. So what we're checking for on all of these graphs is whether or not that right 1 and up 1 point exists, because in all of our parent graphs that we've been dealing with so far, that point is there. And when that pattern starts to change, that's when our a value starts to change. And then we'll look at some that you can't really tell from the graph, and you have to have a more extensive process for. So for this first one, if you're trying to do this as you would in class, I would pause the video and see if you can figure out what this new a value might be. Yeah, maybe you paused, maybe you didn't, but so what I'm looking at here, first of all, this is the rational graph, also called the hyperbola. So the rational is the type of equation. The hyperbola is the name of the graph. Kind of like with the quadratic, the name of the graph is the parabola. So here we have let me get back to this. So this equation is y equals 1 over x for the parent equation. Our locator point is where the asymptotes cross, so right there at 0, 0. And normally we would go over 1 and up 1, and we'd have a point. And our regular one would look something like that. I'm going to undo that so it doesn't screw that up. So clearly we don't have an a value of 1, but what we can look at instead is what happens when we go over 1. We're going up 2. So what we can do then is hypothesize that our a value is now 2. So y equals a, just kidding, y equals 2 times 1 over x. We can also test that theory by using that particular point, that one that's in yellow. That is the point 1, 2. So we can take that x and y and plug them into our hypothesized equation. So 2 for y equals 2 for our a value times 1 over 1. 1 over 1 reduces to just 1, and 2 times 1 is just 2. So we end up with 2 equals 2. So our equation on this one is good. Our a value is 2. And now that I think about it, I haven't talked specifically about what the a value is. Nope, I haven't. I have in other lessons, but let me move this over, and I'll just write it up here. So all of our parent graph equations have, I'll just add another slide. All of our parent graph equations kind of start with this a times x minus h plus k. This particular one is linear. If I make that squared, that becomes quadratic. If I make that cubed, that becomes a cubic. If I take a square root sign over that, it's the square root. Cube root is that. And then the hyperbola that we were just dealing with is 1 over x minus h. In all of these, however, they all have very similar patterns. The h value moves it left or right. And this is in other videos, but just to review. And that's always kind of the opposite of what you think it's going to move. If it's x plus 2, it moves it left. If it's x minus 2, it moves it right. And that can throw people off sometimes. The k value is up or down. And that's kind of exactly the way that you would think it would be. Up or down. Plus k, plus 5 would move it up 5. Minus 5 would move it down 5. The a value is what is called our stretch factor. With a linear, that's simply the slope. But in everything else, that is related to what happens when you go over 1. How many do you go up or down? If you go down, then your a value is negative. If you go up, it's positive. If you go down 2, then your a value is negative 2. If you go up 3, your a value is 3. So that stretch factor, again, is directly related to what happens when you go to the right 1. So let's look at some examples. Our normal cubic, this is the cubic graph, by the way, would go over, that's white, that's not going to help, would go over 1 and up 1. This one doesn't. This one instead goes up 3. So that means that a equals 3. So our graph here, because our locator point, our hk, is 0, 0, this is just going to be y equals a, not a, why do I keep doing that? 3 for a, and then x to the third. This one is our square root graph, so normally y equals the square root of x. Again, this point right here is 0, 0, that's our hk, so we don't have any movement left or right. We go over 1 and up 2, so this time our a value is 2. This one is the hyperbola. Now, instead of our locator point being at 0, 0, it is now up here at negative 4, positive 5. So that means we have an h of negative 4 and a k of positive 5. Remember, with the hyperbola, the rational equation, your locator point is not on your actual graph. It's where your asymptotes cross, and that's what those dashed lines are, and that's what I expect you to draw as well, as your asymptotes on those. So now we need to look at our a value. From the locator point, we go over 1 and we go up 2, which means a equals 2. So our equation is going to be y equals 2 times 1 over x, and it would be minus negative 4, because it's always x minus h, and h is negative in this case. Instead of putting that minus negative 4, I'm going to write it as plus 4. And then our k value is 5, so plus 5. So that's our equation. And we have this test point, this negative 2, 6. We can check and see if that actually works. So if I'm testing this, I can put 6 in for y, 2 is 1 over negative 2 from our x, from that negative 2, 6, plus 4, and then plus 5. So if I simplify, 6 equals 2 times 1 over 2, because negative 2 plus 4 is a positive 2, and then plus 5. 2 times 1/2 is just 1. Drop down the plus 5, and then the equals 6. 1 plus 5 equals 6, so we're good to go. So that is our exact equation. This one, however, we have a new locator point of 3, 4, which is fine. from that locator point, if we go over 1 and we go up, we have obviously not a whole number. So we can hypothesize something for this, but we can also use this point down here as our x and y. So if we write what we think our general equation is going to be, we know this is a cubic, so this is y equals x minus h to the third plus k. I know h is 3 and k is 4, so I can take those out and put in 3 and 4. And then down here, forward, there we go. Down here at this point that we've been given, a passing through point, we have 0 for x and negative 5 for y. So I'm going to take out my x and y as well. And I'm going to put negative 5 in for x and 0 in for, negative 5 for y and 0 in for x. And then I'm just going to do the math and solve. So first I want to simplify, so I'm going to drop down my negative 5. 0 minus 3 is negative 3. And I'm going to show every step here, so just bear with me. Negative 3 cubed is negative 3 times negative 3 times negative 3, so that's negative 27. I'm going to drop down everything I don't use. One really common mistake happens right here. People have a tendency to want to add this negative 27 plus 4. Problem with that is we have a times negative 27, which means these two are attached, and you have to keep them attached unless you divide by that negative 27. So the first thing we actually need to get rid of is this 4. So what we're going to do is subtract 4 from both sides. So we have negative 9 equals a times negative 27. To undo multiplication, you divide by negative 27. And over here, we've got negative 9 over negative 27, so we know it's going to be positive. And then 9 and 27 are both divisible by 3. So if I divide 9 by 3, I get, they're both divisible by 3. So if I divide 9 by 3, I get 3. And if I divide 27 by 3, I get 9. Those are both still divisible by 3. So 3 over 9 is equal to 1/3. And that equals a. And if you look back at our graph, you can kind of see that right there is 1/3 of the way up. But since we're looking at a graph and sometimes that's just harder to do, then we can't always figure that out without doing the algebra. So our full equation, y equals x minus 3, 1/3 x minus 3 cubed plus 4. And that's our exact equation for this graph. Then we can't, So, to sum up, in finding the exact equation, we need the locator point, hk, and one other point on the graph. For example, to find the equation of a rational with a locator point of 2, 3 that passes through the point 5, 4. Our first step is going to be to write the general form of the correct equation. So first off, y equals a times 1 over x minus h plus k. Now, keep in mind, because this is not on the next slide because I was dumb about it, we've got a locator point of 2, 3 and a passing through point of 5, 4. So that locator point, 2, 3, and our passing through point of 5, 4. That gives us our h and k and our x and y. So we substitute those points into our general equation. Once again, that general equation so instead of y, we're getting our, forward, we're going to get this 4 right here. So 4 equals a, and we're going to get our x from that same point, 1 over, my apologies. X is 5, and then minus 3 for h. Nope, just kidding. Minus 2 for h, and then plus 3 for k. And then we need to simplify. So we've got 4, simplify and solve. 4 equals a times 1 over 3 plus 3. I need to get rid of that plus 3, so I subtract it. So I've got 1 equals a times 1/3. Bring this up here so we don't run out of room. 2, get rid of a fraction, you can multiply by its reciprocal. The reason that works is that 1 times 3 is 3, 3 times 1 is 3, 3 over 3 is 1. So that whole thing gives you a times 1, which is what you want. So a equals 3, because 3 over 1 times 1 is just 3. So our full equation, y equals 3 is 1 over x minus 2 plus 3. And this can also be written as 3 over x minus 2 and then plus 3. If that part confuses you, then don't worry about it. Oh, I did this last time too. So that's step 3, that was all the solving we did. And then step 4 is write your full equation. So to do one more example of this, exact equation of a parabola, so that is y equals a times x minus h squared plus k. Locator point 12,9 is our hk. Passing through point is 249, so 49 for y. A, and 2 for x, minus 12 for h squared, plus 9 for k. So 49 equals a times negative 10 squared plus 9. Negative 10 squared is a positive 100. Make sure you are smarter than your calculator in this case. Oops. And then minus 9 from both sides. So we've got 40 equals a times 100. Divide both sides by 100. Those are both divisible by 10, so we can automatically take out those zeros. So we've got 4 over 10. Both of those are divisible by 2, so that is 2/5 equals a. And also write that as 0.4 because it is a terminating decimal. So write our equation. 2/5 times x minus 12 squared plus 9. And that's our final equation. And that's it. Finding exact equation. Have a lovely day.